Imagine an attacker taking down a massive 16-gigabyte enterprise server with a message that's literally shorter than a quick text to your mom.
Just like 11 bytes.
Yeah, exactly, 11 bytes.
Yeah.
Now, imagine the patch for that catastrophic vulnerability was, well, it was issued weeks ago, but your multi-million-dollar security tools are just completely blind to it.
They don't even see it.
Right. Welcome to today's deep dive. We are looking at 3 really critical security reports today from Okta, Checkmarx, and Elastic Security Labs. And, there's a pretty chilling theme that connects all of them.
There really is. It's all about hidden threats.
Exactly. Hidden threats operating entirely within the spaces we just implicitly trust. So if you are tuning in, you're obviously trying to stay ahead in the tech space.
Yeah.
And understanding how information is obscured, sometimes by attackers and sometimes by the software maintainers themselves, is really the only way to actually protect your systems today.
Yeah, the concept of the perimeter hasn't just evolved. I mean, it has completely inverted. What we are seeing in today's intelligence is the active weaponization of the exact mechanisms we rely on for stability.
It's deception across the board.
It is. We are dealing with deception by omission in our foundational infrastructure, deception by infrastructure on decentralized networks, and even deception by steganography right inside our development environments.
Right.
We have to stop just scanning for known bads and start, deeply interrogating the seemingly known goods.
Okay, let's unpack this, starting with that 11-byte server killer. This one centers on OpenSSL, which is, basically the cryptographic backbone of the internet,
Yeah,
right?
pretty much everything relies on it.
So Okta's red team discovered this flaw they've dubbed holobyte. And the mechanics they outlined are just wild.
Huh.
An attacker sends an 11-byte TLS request, and that tiny request tells an unpatched OpenSSL server to immediately set aside up to 131 kilobytes of memory.
For a message body that is never, ever going to arrive.
Right, never arrives.
It is a devastating manipulation of the TLS handshake protocol. To understand why it works, you have to look at the structure of that handshake.
Okay, break that down for us.
So every TLS message carries a 4-byte header. The first byte identifies the record type, and then the next 3 bytes declare exactly how long the incoming message body will be.
Okay.
And what holobyte exploits is a foundational assumption in older versions of OpenSSL, which is basically, it takes the attacker's word for it.
Wait, really? You just trust them?
Yeah. The moment those 4 bytes land, before a single byte of the actual body shows up, before any authentication happens, before any cryptographic key exchange even starts, OpenSSL immediately grows the receive buffer to that declared size.
Oh, wow.
Yeah. The worker thread then just sits there, completely blocked, waiting for data.
On its surface, that sounds like a classic connection exhaustion attack, right? Like slow Loris, where you just hold open a bunch of connections to tie up server
It
resources.
sounds like it, yeah.
But reading through Okta's report, holobyte has a much nastier twist, and it involves the server's memory allocator, specifically GLIP.
Right, the standard C library.
Exactly.
Yeah.
It's not just holding connections open. It's like, imagine a restaurant where a prankster calls up, uses just 11 words to reserve this massive banquet table, and then never shows up.
But instead of clearing the table when the reservation time's out.
Right. The restaurant's management, which in this case is GLIB, refuses to let anyone else sit there until the entire restaurant is just completely shut down and reopened.
That's a great analogy. The underlying mechanism of that allocator is what turns a minor nuisance into a critical failure. When the attacker eventually drops the connection, OpenSSL technically does its job. It frees the buffer.
Okay, so it does release it.
Technically, yes. But GLIB, which handles memory for the system, operates on a philosophy of efficiency. Asking the operating system kernel for memory is computationally expensive.
Right, it takes time.
Exactly. So instead of returning small and medium memory chunks to the kernel right away, GLIB keeps them in a local pool, anticipating that the application will need them again soon.
Which, normally makes sense for a high-traffic web server.
Under normal conditions, absolutely yes. But the attacker varies the claim size on every single connection. They ask for 50 kilobytes, then 112 kilobytes, and maybe 80 kilobytes.
Oh, I see.
Yeah, because the sizes are constantly shifting, GLIB can't efficiently reuse those memory blocks it just freed. The heap becomes wildly fragmented.
So it's just a mess of unusable puzzle pieces.
Exactly. The resident set size, the actual physical memory the process is holding on to climbs rapidly, and it stays climbed long after the attacker has severed the connection.
The numbers from Okta's testing prove how lethal that fragmentation really is. They tested this on NGINX, and a 1 gigabyte server was killed like out of memory killed by the operating system, with 547 megabytes frozen in completely unusable fragments.
More than half its memory just gone.
Gone. And on a larger 16 gigabyte server, HoloByte locked up 25% of the system memory. And here's the real kicker. They achieved this without ever crossing the server's maximum connection ceiling.
Right, which means your standard defenses don't even see it.
Exactly. A web application firewall or a basic rate limiter, they are completely blind to this.
Because standard defenses look for volumetric anomalies, massive spikes in traffic or thousands of simultaneous connections from a single IP.
But this isn't that.
No, this is an algorithmic exhaustion attack. It requires almost zero bandwidth. An attacker could literally run this from a smartphone over a spotty 3G connection and take down enterprise infrastructure. It is incredibly asymmetric.
But okay, here is the part of the report that I really struggle to wrap my head around.
Yeah.
OpenSSL actually fixed this flaw on June 9th.
They did, yeah.
They pushed releases 4.0.1, 3.6.3, 3.5.7, 3.4.6, and 3.0.21, all fixed via pull requests by one of their main contributors, Matt Caswell. But they issued absolutely no CVE, no security advisory.
No changelog entry warning people either.
Nothing. The security team literally classed this as a bug or hardening fix. And to make matters worse, unpatched DTLS datagram TLS operating over UDP remains completely vulnerable. I have to push back on OpenSSL's logic here. Why would they treat an algorithmic exhaustion attack so casually? Especially when, in that exact same release, they issued CVEs for other memory exhaustion bugs.
What's fascinating here is that there is this ongoing philosophical debate within open source security teams about what constitutes a vulnerability versus just, a simple bug.
But taking down a server seems pretty vulnerable to me.
I agree, but sometimes maintainers view resource exhaustion as an operational issue rather than a strict security failure, especially if it doesn't lead to remote code execution.
Wow, okay.
But you have to look at the downstream consequences of that specific administrative decision. The entire enterprise security ecosystem relies on CVEs, the common vulnerabilities and exposures list.
Right.
If you are running an enterprise operating system like Red Hat or Ubuntu LTS, their documented default behavior is to backport security fixes to older, stable versions rather than, moving the entire software package forward.
So a patched package on an enterprise server might still report itself as version 3.0.1, even though it secretly contains the fix from version 3.0.21.
Exactly right. And because of that backporting, the only way automated security scanners know a system is vulnerable is by reading the OVFL feed, the Open Vulnerability and Assessment Language.
Which is the standard XML feed those scanners use.
Right, and it is keyed entirely to CVE identifiers.
So if OpenSSL decides not to issue a CVE, there is no entry in the OVL feed. All those automated multi-million-dollar vulnerability scanners out there are just looking right past this critical flaw.
Yep. Without a CVE, there is no identifier for a scanner to match. There is no advisory for your security team to read. The practical impact for you listening to this deep dive is that you cannot rely on your automated tools for this specific flaw.
You actually have to go manually verify it.
You do. You need to manually verify if your OpenSSL builds are based on those June 9th releases, or if your specific Linux distribution maintainer pulled in the patches independently.
And if you compile it yourself.
Then you need to upgrade and manually restart whatever processes loaded the old version in memory. A silent patch in foundational infrastructure creates a massive, invisible blind spot.
Well, that blind spot in our automated tools is exactly what threat actors are banking on right now. Not just with silent patches, but with the very infrastructure they use to attack us.
Oh, absolutely.
Which brings us to the Checkmarks report on Vite Venom. This takes the concept of invisible threats and applies it to the software supply chain.
Yeah, the Vite Venom campaign represents a highly sophisticated evolution in how attackers distribute malware today.
Tell us about it.
So researchers discovered a cluster of 7 malicious NPM packages specifically targeting developers who use Vite.
Which is super popular right now.
Oh yeah, it's become one of the most popular front-end build tools in the JavaScript ecosystem because of how fast it handles native ES modules.
Oh. So this campaign was published in late June and early July of 2026, linked to a threat actor named SuccessKey. And it actually expands on a previous attack known as Chainveil.
Right.
But what caught my eye immediately is the naming convention. Like, older supply chain attacks relied heavily on typo squatting, hoping a developer just types React with 2 C's instead of React.
Right, relying on fat fingers.
Yeah. But Vite uses scoped package names, like at Vite.js plugin something, to impersonate the official namespace. To a developer reviewing a package.json file, it looks completely legitimate.
Yeah, the scope namespace is a really effective social engineering layer, but the technical hook here and what makes it so dangerous is how the malware actually executes.
Okay, how does it run?
Historically, malicious NPM packages relied on install scripts. The malicious code would execute the moment the developer or, the CI/CD pipeline ran npm install.
Right.
But endpoint detection and response tools EDRs have caught on to that. They heavily monitor that installation phase now.
So the attackers changed tactics.
Exactly. Vite bypasses this entirely by executing at import time rather than install time.
Wait, really? So the malware just sits there dormant on the hard drive after it's installed?
Just waiting.
It only fires up when the developer actually writes an import statement in their code and spins up the local development server.
Yes. That execution shift severely limits endpoint security detections. By the time the code runs, the build process is already well underway. The malicious activity just blends in with the massive amount of file reading and network requests a modern front-end framework makes during compilation.
Here's where it gets really interesting, though.
Yeah.
The network requests it makes. Once it executes, Vite doesn't reach out to a standard web domain or some rented cloud server to download its payload.
No, they went decentralized.
Yeah. It uses a 4-tier blockchain command and control infrastructure. It literally spans Tron, Aptos, and the Binance Smart Chain to deliver a remote access Trojan. They are storing the payload pointers as transaction data on public blockchains. It's like, imagine writing a bank heist plan in classified ads on a giant, indestructible public billboard. Law enforcement can see the message, they can read the code, but they literally cannot tear the billboard down.
That is the perfect way to look at it. If we connect this to the bigger picture, it solves the biggest point of fragility for any threat actor, which is their own infrastructure.
Because usually, defenders can just take down the domain.
Exactly. Historically, if a security researcher found a C2 domain, they could report it to a registrar, get it sinkholed, or just block the IP address at the firewall level. But blockchains are, by design, immutable and decentralized.
You can't just call up the CEO of the blockchain and ask them to delete a transaction.
Right. By moving the payload retrieval instructions to smart contracts and transaction memos on these networks, the attackers have made their infrastructure practically uncensorable.
And the redundancy they built into this is just wild. According to the report, if the primary Tron-based retrieval fails for some reason, the malware automatically falls back to querying the Aptos blockchain.
It just keeps trying.
Yeah, and if that fails, it queries the Binance Smart Chain. Only as an absolute last resort does it fall back to a traditional HTTP fetch from a standard domain.
Attackers are treating their malware delivery with the same high-availability architecture that, Netflix uses to stream video.
Which is terrifying. So how are developers supposed to defend against something that fires the moment a library is imported and relies on uncensorable infrastructure?
It requires a layered defense strategy. The immediate practical impact for you listening is that dependency auditing must go deeper than just looking at the namespace. Attackers are successfully compartmentalizing their distribution tracks, specifically to bypass the trust we place in scoped packages.
Right. So if a developer realizes they've imported one of these at Vite.js impersonators, what is the cleanup process? I imagine just deleting the package from the node modules folder isn't enough.
Right. Not at all. If you suspect exposure, credential rotation is obviously step one. But crucially, you have to check the developer's environment files.
Which one specifically?
You want to look at .bashrc, .zhrc, and .profile files on Linux or Mac OS.
The ones that load when you open a terminal.
Exactly. These files dictate what happens every time you open a new terminal window. The remote access Trojan delivered by Vite specifically targets these files, injecting unauthorized bash scripts to maintain persistence.
Wow.
Yeah, so even if you completely wipe the project directory and remove the malicious package, the backdoor remains embedded in the developer's operating system environment.
So attackers are moving from public, indestructible billboards on the blockchain right into the most private, intimate spaces of a developer's machine.
They're getting brilliant at hiding in plain sight.
Which brings us to our final story for this deep dive. We've talked about infrastructure hiding on decentralized ledgers, but Elastic Security Labs uncovered an operation that hides devastating malware right in front of a developer's eyes during a one-on-one job interview.
Right. This is the Contagious Interview campaign. It's run by North Korean state-sponsored actors, specifically the group tracked as REF 9403.
And it targets developers directly.
Yes, it represents a highly targeted, deeply personal social engineering vector that preys entirely on professional ambition.
The intelligence outlines a scenario that plays out in tech every single day. These attackers infiltrated a community Slack channel. A user going by the name Maxwell posted fake jobs looking for experienced Next.js and Nest.js developers.
It happens all the time.
All the time. When a candidate takes the bait, they move to direct messages, and the candidate is asked to complete a standard coding assessment. We've all been there. You get a GitHub repo, you're told to build a feature or fix a bug over the weekend to prove your skills.
It is an incredibly effective lure because it exploits the inherent trust we place in the hiring process. The developer clones the repository, runs npm install, starts the local server.
And the project actually works.
It does. As the Elastic report notes, it looks and behaves like a legitimate modern web application. There are no glaring errors or broken dependencies, but it is hiding a massive secret using steganography.
So what does this all mean for the listener? Steganography is basically the practice of hiding data within other data, right?
Yeah.
It's like writing a bank heist plan in invisible ink between the lines of a child's coloring book. The security scanner just looks at the file, sees a coloring book, and lets it through.
That is an excellent way to visualize the mechanism. In this specific attack, the coloring book is a set of standard SVG image files representing country flags.
Like just normal flag icon.
Yes, files named ae.svg or af.svg sitting innocently inside the repository's web assets directory. SVG files are essentially just XML text files that tell a browser how to draw vector graphics.
Okay.
To the naked eye and to most automated security tools, they render perfectly as small pixelated flags on the screen.
But the invisible ink is hidden inside the code of those images.
Yes. The attackers took their malicious payload, split it into base64 encoded fragments, and embedded those fragments inside standard HTML comments within the raw XML of the SVG files.
Oh, wow. So just inside the comments.
Yeah, and a browser ignores HTML comments when rendering the image, so the flag looks completely normal.
But wait, if the code is just sitting in a comment, it's dormant. How does it actually execute and infect the developer's machine?
The trigger is a seemingly benign JavaScript file in the repository named servervalidation.js.
Okay.
Every time the developer boots the local server to test their code, that script quietly traverses the assets directory. It parses the SVG files, searches for the specific HTML comments, extracts the base64 fragments, pieces them all back together in memory, decodes them, and executes a 4-stage payload.
And the developer has absolutely no idea it's happening in the background.
Not at all.
That payload is a piece of malware known as OtterCookie. And OtterCookie is nasty. It drops a socket.io remote access Trojan. Socket.io uses WebSockets to maintain a persistent real-time connection back to the attacker, allowing them to quietly funnel data out of the machine.
It's very stealthy.
It steals crypto wallets, it scrapes browser data, it grabs clipboard content. But there's a very specific detail in this report that we need to zero in on. Among the files OtterCookie specifically targets are AI coding tool extensions and configurations.
Right. Things like .claude, .cursor, .gemini, .windsurf, .pari, and .llama.
Why are these DPRK actors so interested in stealing data from tools like Claude and Cursor? Are they after source code or the automated credentials these AI tools hold?
This raises an important question, and it really represents a massive shift in targeting priorities for state-sponsored actors. To understand why they want these specific files, you have to look at how AI development tools function on a local machine.
They need context, right?
Exactly. Applications like Cursor or Claude's desktop app need to understand the full context of a developer's workspace to generate useful code. To do this, they create local indexes, cache prompt histories, and often store session tokens or API keys in local SQLite databases or plain text JSON files.
So they aren't just trying to steal the specific code the developer is writing for the fake job test. They're going after the keys to the kingdom.
Precisely. By targeting AI tooling configurations, these North Korean actors are stealing the developer's augmented workflows. If an attacker can exfiltrate those local AI context files and session tokens, they can potentially impersonate the developer's AI session.
That's terrifying.
They gain access to the proprietary systems the developer interacts with daily, the API keys stored in their workspace, and the massive amount of context the AI has indexed about their employer's actual codebase.
They are essentially stealing the developer's second brain. which makes the individual developer the single most valuable target for a supply chain attack.
Developers themselves are the new perimeter. The days of securing just the production servers or the main corporate repository are over. A single compromised developer sitting in their living room doing a weekend coding test for a fake job on their personal machine can inadvertently hand over the keys to massive downstream enterprise infrastructure.
So you have to treat every third-party assessment repository as fundamentally hostile. Do not trust it just because it runs without errors.
Absolutely not.
This brings us full circle today. As we synthesize today's intelligence, the common denominator across all three of these stories is that service-level trust is a massive, exploitable vulnerability.
It really is.
We saw OpenSSL failing to issue CVEs for critical memory exhaustion bugs, essentially blinding our automated security scanners. We saw Vite hiding unkillable C2 infrastructure in plain sight on public blockchains, executing only at import to bypass installation checks.
Yep.
And we saw North Korean actors weaponizing the hiring process, using steganography to hide devastating WebSockets RATs inside the HTML comments of simple vector images.
It is a thriving ecosystem of hidden threats. Deception by omission, by infrastructure, and by steganography. And it really forces us to reconsider how we validate every single line of code we interact with, which, leaves us with a critical and perhaps uncomfortable thought to consider moving forward.
Let's hear it.
If immutable blockchains now serve as bulletproof hosting for malware, and standard image files can silently assemble remote access Trojans during a routine everyday code test, are we approaching a future where human code review is entirely obsolete?
Wow.
Think about the trajectory here. If attackers are successfully hiding malicious payloads in the metadata of vector graphics, a place no human reviewer is actively checking, will the future of developer security demand that every single byte of third-party code, even a simple image file, be executed in an isolated, AI-monitored sandbox before it ever reaches a human screen? Because right now, the attackers are banking heavily on human trust and human oversight to slip right past our defenses.
That is a terrifying but entirely necessary question. As the tools we trust are turned against us, the hiding spots are getting smaller, more sophisticated, and infinitely harder to detect with the naked eye. That concludes today's deep dive. Take a hard look at your development environments, manually verify those OpenSSL versions, and remember, stay curious, stay paranoid, and keep your systems secure.